everyone. So myself Kipna. Today I am here. Me and Vidisha are here to present here about the Big Bang theory.
So, starting with the presentation, in this session, we would be studying a brief autobiography of our universe, that is from nothing to everything, how everything started and is still in the position of being studied like this. So, moving forward, also in this question, we would be addressing some of the big questions that people have been asking from thousands of years, like how did our universe started, what triggered it, why is it still in place, everything, the galaxies, planets, why are they like we observe from the telescope, and how will everything end, or is there a different future of universe. So before going deep into it, we have a meme here that if ever we decide to celebrate our universe birthday, then we actually need 13.8 billion candles, because that's the estimated age of our universe. In the later slides, we will also see how this age was estimated. So what is Big Bang? Like, what comes to your mind when you hear this term Big Bang? Is it the beginning of everything, or do you believe it is just a misconception? Think for a moment. So, many of you must have guessed it as an explosion in empty space. That's the myth. Many people still believe that. But actually, it was not an explosion, it was an expansion of the entire space. No center, no edge, nothing, just the expansion of the entire space. Also, it does not have a center or a specific place where it happened. Basically, okay, so um, let's try to think it like this. If there is a balloon and I draw two dots on it, and after inflation, the distance between the dots will increase. So it was not that the two dots move away from each other, it was basically the entire surface which was expanding. So you can relate these dots as to any two galaxies, and this balloon surface as the entire universe. So yeah, moving forward, yeah, so this term Big Bang, it was not something which was given very mindfully. It was basically uh, okay, think about it. Why does only Big Bang, not big origin or big expansion? It was not something which was decided before. Only after a radio interview by Fred Hawley, he coined this term Big Bang, and this term stuck forever. Although he ironically he took that in a sarcasm, because he didn't believe in Big Bang. Like, what rubbish! There's no such expansion or something like that. So till now we have seen that Big Bang is a model which describes the beginning of expansion of a universe from a very extremely hot and dense state. With the balloon analogy, we also relate it with expansion and not explosion. And this is important to remove this myth that it's not explosion. And everything, matter, energy, space, time, everything started with this massive expansion. So time, as in this age of universe, that is 13.8 billion years, it is also estimated from that time when expansion started and not before that. So we don't know what was before that, how many years before that tiny dense hot state was existing and everything like that. It's still a mystery. Moving forward, we have origin of universe. It will be explained by Kirtana.
Going to the universe origins, we need to think about the question that what was there before the Big Bang? That's actually one of the biggest mysteries in science still today. Many people think that the Big Bang explains how everything was created from nothing, but that's not exactly what scientists say. The Big Bang theory mainly explains how our universe changed and evolved from an extremely hot and dense state into the huge universe we see today. As we said before, for the question what happened before Big Bang, we honestly don't know the answer yet. Even many scientists believe that this question doesn't even make sense because they believe that time itself may have started with the Big Bang.
So, if you see at the superficially at the events that occurred, so started with tiny glowing point, that was that extremely hot and dense state, which expanded and then cooled to form subatomic particles, which later form atoms, stars, and finally galaxies, and then us. So now it's the cosmic timeline. Kirtna will continue from here.
So we have talked about what the Big Bang is. But have you ever wondered how we got from a tiny hot universe to this huge universe filled with billions of galaxies? So the entire story of the universe can be explained in this one image. Notice something here that this picture gets wider as we move to the right. So it indicates that as the time passes, the universe becomes larger and larger. It's nothing but symbolizing universe is expanding. So let's quickly travel through 30.8 billion years of the universe story. Starting with the initial stage, it was the Big Bang. Everything begins over here. Later, the next stage was the formation of atoms. After about 380,000 years later, the universe cooled enough for the atoms to be born. So we will see what are the atoms that are born in the next slide. And then came a period called cosmic dark ages. So what does this dark ages mean? It's nothing but at that time there were no stars in the universe and the universe appeared mostly dark. So it was named as the dark ages. So eventually, gravity formed the stars, bringing light back to the universe. So those stars gathered into galaxies, and over some billions of years, galaxies continued to evolve. And finally, after 13.8 billion years, we arrive at the universe that we see today. But humans have existed for only about some 300,000 years. So we can say that we are a very very recent chapter of this universe story.
Moving forward, so as the universe cooled with time, it also allowed the formation of more complex structures. We will see it later as well. So now, all this Big Bang, expansion, origin, everything, it sounds so fascinating. But this thought must came to your mind that I was not there, you were not there, no one was there. Who knows what actually happened? Is there like any proof to it or any evidence? So we have a handful of evidence that can prove all this, that universe was formed after expansion and it is still expanding. uh, we will see five of them. So the first one is Hubble's law. So Edwin Hubble was a scientist who observed the galaxies moving away from us by his Hooker's telescope. So before this, the scientists believed that the universe is static, it's stable, and the expansion is has stopped. It is not still expanding, but it was only after ex. His observation and comparing the results that we got to know it is still expanding. And he also gave his famous equation, that is v is equal to h naught d, v being the recession velocity, the speed with which galaxies are expanding away from us, then h is the Hubble's constant, and d is the distance from the center. So from this relation we can conclude that v is directly proportional to d. That is, if the distance is increasing, the velocity will also increase. Therefore the farther galaxies are are expanding faster than the ones nearer. So yeah, moving forward, next is cosmic microwave background. So it is basically the ancient most light that we can observe. It is basically the radiation from the early universe in the form of microwaves that gives us information about many things like composition, age, temperature, rotation, magnetic field, and many more such things. So I will first explain why the temperature, as mentioned here, 2.7 Kelvin, because it is way cooler than what we are expecting at that time during Big Bang. Okay, before this, just think for a moment, if we can perceive perceive this ancient light and gain so many information from that, why can't we see Big Bang till date? Think for a moment. Okay, so it is because this light is not from the time of Big Bang. It is almost about 380,000 years ago that this light started moving freely and reached us. So before that, after Big Bang, the just after Big Bang, the subatomic particles w- filled the entire space and the light could not move freely at that time. So it was only after the formation of atoms and nuclei that this light got the freedom to move freely, that and reached us. So that's why we can't see Big Bang. So coming to the temperature thing, at the time of Big Bang, the temperature was nearly almost of the range of 10 to the power 22. That is at this time. When the time 380,000 years I'm considering, at that time when the light got the freedom to move freely and reach us, at that time the temperature was somewhere around 3000 Kelvin. And at now when the light reached us in the current times, the temperature is 2.7 Kelvin. So why was there a change in temperature? Why did it decrease like that? So as mentioned earlier, since these are in form of microwave radiation, so microwave have a very large wavelength. As the wavelength increases with time, that also we will see why the wavelength is increasing. So as the wavelength increases, the energy decreases, and so does the temperature. So this thing why the wavelengths are increasing, we will see in the redshift part in the upcoming slides. So that was about temperature. Now, how come we can estimate the age from it? So studying the radiation. Okay, first let me explain the Doppler's effect. So Doppler's effect is basically blue shift and red shift. When a planet, when a star or some celestial object is coming towards us, the light from it starts shrinking, and because of that shrink, the wavelength decreases, and so it is known as blue shift. And vice versa, when a star is moving away from us, the light emitted from it also starts to stretch, and the wavelength increases. This phenomena we term it as redshift. So because of this redshift and the expansion pattern, putting all this in an equation, studying the redshift, the wavelength, and the expansion pattern, putting all this in equation, scientists actually estimated the age of Big Bang, the origin of universe, to be 13.8 billion years. So yeah, also this branch of physics or astronomy which studies light in, to gain information, this is known as spectroscopy. From spectroscopy we can find more such information like the composition, as in for example, if a star contains hydrogen, hydrogen has one electron, so when light passes through it, this electron gains energy for the to jump into the higher energy level. So that light, so it absorbs that component of light which corresponds to the energy difference of these two energy levels. And from the emitted light, when we study this spectral line, so that component is missing. And when we match the spectrum, so we get to know that it was hydrogen which absorbed that component. So like this, from spectroscopy we can gain information about the composition of different stars and other celestial bodies. Also the magnetic field, as mentioned before, the spectral lines coming from this, if there is a magnetic field, then the spectral lines split, and and if the splitting is directly proportional to the strength of the magnetic field. That is, if the magnetic field is strong, the splitting would be more, and vice versa. Also this also gives information about the direction of magnetic field, as in normally the spectral lines are randomly arranged, but when they are in magnetic field, they first of all split, and this effect is known as xenon effect. Also these splitted lines are polarized, that is, they are arranged in a particular direction, and this direction gives us information about the direction of magnetic field. Moving forward, also, how can we gain information about temperature of a particular star? uh, Imagine you, I have a hot iron rod, like red hot iron rod, and I didn't mention that it is hot, but you will still get an idea that it is hot because it turned red. In same way, different stars emit different radiations, and uh, observing those radiations, we gain the information of their temperature, matching those radiation coming from them with this lab spectra. For example, if there is one star which is very hot, extremely hot, these stars usually emit UV rays or X rays. Mediumly hot star, they emit infrared rays. And cool stars, although they are not as cool as it is termed, but yeah, relatively cooler stars, they emit microwave rays. So if you observe the pattern, as the temperature is decreasing, so is the frequency, or you can say the wavelength is increasing. So we can relate it with the wavelength as well. Moving forward, it's Big Bang nucleosynthesis, like the formation of first atomic nuclei within the first few minutes just after Big Bang. So hydrogen was produced, helium was produced, and some tiny traces of lithium were also produced. Okay, so although I'll answer it later, but just think about it for a moment. Why only these three elements were formed and not other like carbon, oxygen, or nitrogen? Why weren't they formed? Think for a moment. Okay, so, well, just in the first 20 minutes, the universe was cool enough that it could not provide the conditions for these nuclei to fuse and form heavier nuclei. That is, so these as you know, hydrogen has only one electron, helium 2, and lithium 3. So these are very small atoms. So initially these three were formed, but as the heavier ones were about to form, the universe cooled at the initial 20 minutes. So it was later on, only after the formation of stars, that these heavier nuclei were formed in their cores, which provided extremely hot conditions for these lighter nuclei to fuse into each other and form heavier nuclei like oxygen, nitrogen, or carbon, and etc, etc. Moving forward, okay, so a Big Bang gave the ingredients, and star made the cooking. Moving forward, we have expansion of the universe, which will be explained by Kirtana.
away from us. As it's uh, as we are moving away from us, we can say that universe is expanding.
Now it's the cosmic web. It will be continued by her.
So coming to the cosmic web, we have some billions of galaxies in the universe currently. So you might wonder, uh, how are these galaxies arranged in the universe? It might be, is there any something specific way or arrangement? But the answer was, they are arranged something something called a structure called as cosmic web. So what's cosmic web was? Gravity slowly pulled those all galaxies together, forming long chains. Those are called as filaments. And these filaments connects groups of galaxies to form clusters and superclusters. Yeah, as you can see in the images, that the both of the images represent the cosmic web structure. In those images, you might notice something else also. What's that? There are many empty regions in between those filaments, and those are called as cosmic voids. Those are the dark patches. They also contains galaxies, but as compared to the rest of the universe, they contain pretty much less galaxies. Also, there is an amazing fact that was, we might think universe contains many galaxies, stars, and other planets, but it's not true. The universe has these type of filament structures a large more than this. So moving ahead,
So we have this 3D visualization model of the cosmic web. You can just observe it for a moment. So moving forward, as discussed by Kirtana, redshift and these large scale structures, these cosmic web. So all five of them, if I recall all of them, we started with Hubble's law. So it proved that the universe is still expanding from the observation and from his equations as well. And cosmic microwave background, that is the ancient most light, it also gives us information about the ancient universe. These elements, hydrogen, helium, lithium, their existence in the earlier times, in the most ancient times, confirms that theory of Big Bang is still relevant and existing. Because if the universe was not as we have studied, like it cooled in the initial 20 minutes, it was extremely hot before that, all this, and later on the stars formed in their cores, the heaven nuclei were formed, all this, if this all did not exist, then the relevance for these initial three elements, their formation, wouldn't have been existed. Then redshift, as mentioned earlier, redshift is when a star or any other cosmic object is moving away from us, and we have observed this redshift in spectrometry of a lot of stars. So this is also confirming that universe is still expanding. And the last one, the last scale structure. So there were many simulations which were based on Big Bang, and when they were observed and concluded, the results were similar to what we are observing in today's in telescope for the universe that is existing today. So this also confirmed the existence of Big Bang. And out of all five of them, none of them individually can prove the relevance of Big Bang, but combining all five, they hold a strong proof to support this theory. So that's it for the evidence part. Now, moving forward, we have some fundamental forces. So, as we know, there are four fundamental forces: gravitational force, strong nuclear force, weak nuclear force, and then electromagnetic force. So, yeah, gravitational force, as we all know, is that force which is applied by every two object in this universe which possess mass. It is inversely proportional to the square of distance. This strong nuclear force is the force holding the atomic nuclei and electrons in place. Weak nuclear force is involved in atomic decays and nuclear reactions, all that. Electromagnetic force. Okay, so here is one question. As we have proved earlier that universe is still expanding, so why is it that we are not expanding, and why are we at the first place existing if everything is expanding? Even our the atoms, the matter inside us should also be expanding. So why is it that we are still existing like that and not expanding? Think for a minute and we will continue from here. You can get a hint from just now. I have read this electromagnetic force. So it is because of electromagnetic force which holds all the atoms together. And also it is responsible for the for light as well. So this electromagnetic force, it is the reason that we are not expanding like the universe is. So this effect of expansion, we will see the cause for it later on as well. So this effect of expansion is only limited to large celestial objects and not us. And okay, so from the time of inflation, something in respect to these fundamental forces also changed. So before, when the conditions were extremely high, then all these fundamental force were combined. They were just one force. When this expansion happened, the four fundamental forces became distinct. And that's these four forces that we know today. So at one point of time, all four of them were just one. Moving forward, okay, so matter antimatter mystery, which is famously also known as Bayon's asymmetry problem, we will see that why it is a mystery. So according to physics, okay, starting with what is matter. We all know matter is something which has mass and occupies space. All of us know it from very junior classes. But what is antimatter? So you can imagine antimatter as something which is contradictory or opposite to matter, like fire and ice, or friend and enemy. You can say these two, matter and antimatter, are evil twins. So according to physics, when these to matter and antimatter, they meet, they destroy each other and also produce a lot amount of energy. And this process of their meeting and then destroying each other into energy, this process is annihilating. So according to physics, both of them were produced equally. And here comes the mystery. If equal amounts were created, then why is our universe made almost entirely of matter? Again, we will take a pause of a minute and you guys please think about it. Okay, so the answer is here in the slide itself. It is almost and not equal. Please mind this term, almost equal amounts and not equal. So imagine if there are 1,000 soldiers and 1,000 enemies, and the trick is that each one of them kill each other in pair. So all of them, after the war, all of them will die. But if the cases change and there is 1001 soldier and only 1000 enemies, so this one will remain after the war. So is the case with this mystery. Actually, it is a mystery because we don't know why they were not produced in equal amounts. But here is the thing, because there was one extra particle produced per billion pair of matter and antimatter, and because of this one extra particle in every billionth pair, that everything we see today is existing. So yeah, it is a, that's why it is known as asymmetry problem, and it is a mystery why they were not produced in equal amounts. So that was interesting. Now moving forward, okay, now we have formation of atoms, which will be continued by Kirthana.
So, previously we have seen the cosmic timeline over which, after the Big Bang, the next stage was the formation of atoms. So, studying about this formation of atoms, we might think what's before that. So, the early universe was extremely hot, that is, about some millions of degrees temperatures was maintained at that time. And at such high temperatures, there were some subatomic particles like electron and proton, and they were moving so fast that they couldn't form a stable atom. So that's why instead of atoms, the universe was filled with these elementary particles along with the plasma. So now what had changed? So what's after? As we know that universe started expanding, it is also cooling down simultaneously. Once it became cool enough, the protons actually captured those electrons and led to the formation of an atom, like hydrogen atom, helium atom, and the traces of lithium. So now finally hydrogen atoms and helium atoms have been formed. The other important part over here is the transparent universe. So before atoms formed, the light is kept crashing into these free particles and couldn't travel very far. So these are acting as obstacles for the traveling of light. But once these electrons were locked inside some atom, and then the number of free electrons in the universe decreased, so there are no chance to block the light from traveling. So for the first time ever, the light could travel freely across this universe. That's why scientists coined this term as the transparent universe. A simple analogy for this can be, if we try to shine a flashlight in a foggy room and light can travel, we might say that it couldn't travel because that foggy layer will act as an opaque object and restricts the traveling of light. But once we have performed this experiment in other room which has no fog or something, then observing the traveling of light, we can say that it travels steadily without obstruction. So this can be about the formation of atoms. Going ahead, after the formation of atoms, we have other stage, that is the formation of stars and galaxies. So previously we have seen the formation of atoms, and those atoms which are formed were like hydrogen atom and helium atoms. Now you might think, how did these tiny atoms, hydrogen and helium are the tiny atoms as we know, they were placed on the top of the periodic table too because of their size. Okay, because of their size, how could these tiny atoms could form into a stars and galaxies? You can see the image over here, that is the nebula. It's nothing but a massive cloud of hydrogen atoms and some cosmic dust involved in space. Over there, gravity acts. The gravity do is, the gravity pulls those hydrogen atom clouds together and together, and it tries to such that center temperature becomes somewhat about some 15 million degrees Celsius. So that temperature is suitable for a process to occur. That process was nothing but the nuclear fusion. We have studied about this in our 12th standard, that a combination of nuclei leading to a new atomic nuclear releasing some enormous amounts of energy. So that process has been done here, and out of this process, the product was the star. At that moment, we can say that star was born out of from these atoms. So now also gravity keeps working, and these billions of stars came together to form enormous systems, and that can be called as galaxy. Also, there is a fun fact over here. What's that is, the calcium in our bones, the carbon in our body, even the oxygen we breathe are all made or all created from these stars only. So, sarcastically, we can say that we are born out of this stardust. Moving ahead,
So now we will study
going
something.
to the dark matter. Firstly, imagine you are a scientist observing a galaxy which is some million light years away. It's very distant. So you now calculate how much matter is in the galaxy by counting number of stars you can see. It wouldn't be feasible, just imagine. So now you will calculate based on number of stars, you will calculate how fast they may rotate. Think for a while. So you may come to some conclusion that they will travel with some velocity. So, but that's not the reality. The reality is that the stars are moving much faster than they should. Why that's happening? Okay, we'll go into it. According to that, gravity produced by these visible stars, these galaxies should fly apart. This galaxy should fly apart because the gravitational force wouldn't be sufficient enough to hold them together. But we see that these galaxies are not flying away. So, what might be the reason? What is responsible for these galaxies for flying apart? to get together? The answer seems to be something that we cannot see. That's the dark matter. It's nothing but a matter, a kind of matter which does not emit, reflect, or absorb the light. So you might think that if we can't see, how can we say it does exist? We can prove its existence by its effects only, because the galaxies are like packed in together and they are not moving apart. So we can say that this dark matter acts like a invisible glue which helps in holding these galaxies together. Going before,
So now, since you gained a basic idea of what dark matter is, now we will see three of its effect that can prove that there is something as dark matter which is existing. So starting off with galaxy rotation curve. So according to the Newton's law of gravitation, we know it is the force of gravity. It is inversely proportional to the square of distance between the two objects, and because of it, the farther stars should move at a very relatively slower speed as the nearer ones are moving. But in observation, we have observed that both of them are moving with almost the same velocity. So can you relate by any chance this with dark matter, with the existence of dark matter? Well, yes, we can. And yeah, so visible matter cannot produce this amount of cannot explain this observation, and it is dark matter which comes into picture, and it surrounds the galaxies in a massive halo. Halo is as in a ring-like structure, almost a ring-like structure, and it provides the necessary extra gravitational pull for the farther stars to orbit with the almost the same pace as the nearer ones are doing. So moving forward, we have another effect, gravitational lensing. So before starting off directly with this, let's imagine a large rubber sheet which you have like stretched a rubber sheet, and I came with a very heavy ball and I kept it in the center. So what will happen, the sheet will at that point at the center where I have kept the ball, at that point the sheet will actually bend down, and then I come up with another idea of putting a marble at the edge, and the marble will follow the curved part as a result. So you can relate this with the marble with the light coming from distant stars towards us, the this ball as the matter in the universe, and yeah, that rubber sheet as the space fabric. So according to Einstein's general relativity, mass bends space and light follows the curved path. So as a result, light coming from distant galaxies bend around massive objects. So there's one more outcome of this, that this light which is bent before reaching us, since it is bent, so it is formed the images obtained from it are not perfect, and sometimes they are distorted, stretched, or sometimes duplicated as well, sometimes in ring shape also. We call that famously the Einstein ring. And okay, that all this is fine, but here is yet another thing. So why is it important, like why are we studying this under the dark matter thing? So it is because the visible matter that we see in the universe cannot produce this much amount of bending that the light coming from stars, distant stars towards us, that light is experiencing some bending, actually a lot amount of bending, that then the actual matter, visible matter in the universe can actually produce. So this uh, points towards the existence of dark matter, which is providing that extra bend again. So yeah, so you can just remember this as this slide as just bending of light, that's it. Rest all is explanation. Moving forward, why galaxies need dark matter. So I think you get an idea of this from the previous slides, that why does galaxy, what extra purpose that is the dark matter serving to us that is useful. So why the galaxies are not escaping out, since they are orbiting at so high speed. Imagine this as spinning a bucket full of water. So as you spin it faster and faster, the water will eventually fly out. So similarly, the galaxies are supposed to escape out from the edge, but in observations they are not. So it is the dark matter which is providing extra gravity, or you can say additional gravity, which is putting everything in place. So yeah, that's it, these four things that providing extra pull to the galaxies at the edge so that they could not escape out, gravitational lensing and galaxy rotation curve, these are the three effects of dark matter that are being observed. Moving forward, we have dark energy. So it will be continued by Kirthana.
So, in the before slides, we have learned that the dark matter acts like invisible glue, holding these galaxies together with the help of gravity. But now comes an even bigger mystery. What if I say you that there is something in the universe that's doing the exactly opposite? Yeah, you have heard right. Astronomers discovered that universe isn't just expanding. Instead, it's expanding even more faster and faster. In other words, we can state it as some expansion acceleration, or expansion of the universe is accelerating. Something seems to be pushing these galaxies apart, and we call this mysterious effect as dark energy. So dark energy was responsible for the galaxies to move apart. By today, dark energy makes up about some 68% of the entire universe. But still, there is something that we don't understand perfectly about this dark energy. We can learn about this dark energy in the coming slides.
So just like dark matter has its effects, dark energy also has its effect in accelerating the expansion. So earlier we have studied that this universe is still expanding, but I didn't mention, or we didn't talk about the rate of this expansion. So most of you must have thought that it is expanding at a fixed speed or defined speed, but it is actually expanding in accelerating motion. So the expansion is accelerating, and this possible explanation for this is dark energy. So earlier it was expected that gravity will slow down the expansion, but it was recently observed that a distant type supernova showed the expansion is actually speeding up. And as mentioned, it is effect of dark energy, which is almost 68%. And just like dark matter give provides additional gravity, this dark energy, it opposes the gravity and helps in driving the accelerated expansion. So moving forward, we have lambda CDM model. It is basically, just imagine it as a standard model of cosmology that we are following, and it explains the expansion of universe CMB, that is cosmic microwave background, the ancient most light. And it also talks about formation, describes formation of galaxies, about dark matter and the existence of dark matter and dark energy. And this lambda CDM model, it basically have three blocks. We will talk about it in the next slide. So the lambda one is the lambda, which represents dark energy, and as mentioned earlier, it helps in accelerating the expansion of universe. CDM stands for cold dark matter, the invisible matter we just talked about in a few past slides, that provides additional gravity and helps in forming the cosmic web and galaxies, everything. Then it is ordinary matter, which is nothing but the visible matter, the stars, planets, gas, dust, and even us, everything that we can see and not, which is not invisible. And it accounts for only 5%, approximately 5% of the universe, whereas the other two, that is the this dark energy and dark matter, these two, the dark energy accounts for almost 68%, whereas dark matter accounts for 27%. So moving forward, well, now we have studied the origin of universe, how it started from just a very tiny, extremely hot, dense state, everything. Then how it expanded. Expansion is still speeding up because of dark energy. Everything is being held at place because of dark matter. We also studied the timeline, evidences supporting Big Bang, the fundamental forces, and formation of atoms, stars, galaxies. We even saw the asymmetry problem, that is the matter and antimatter mystery. And yeah, we saw the effects of dark matter, dark energy, lambda CTM model. But now there's one question that pops in many of our mind, that that's it, or is there something more to it? As in, what will be the future of our universe? How will it end, or will it even end, or whatever? So there are basically three predictions for the universe to end: big rip, big crunch, and big freeze. Starting with the last one, the big rip, it is basically predicted that maybe the expansion becomes so strong, as in the dark energy dominates everything, that everything, galaxy, star, planet, and even the atoms torn apart, and everything will end like this. So sounds scary, but so next one, big crunch. It is weird, but it is believed that expansion may reverse and universe will collapse into that tiny, small, dense, extremely hot state. It is kind of weird, but coming to the last one, the big freeze. So this term, the big freeze, is kind of you can say kind of misleading, because many people think the universe may freeze, but it is not so. Expansion will continue forever, and since the matter in our universe is conserved, as in mass is conserved, so matter is limited, so stars will eventually burn out, and since everything will move apart, so stars will burn out, and hence no new stars will be produced, and eventually everything will be very dark, empty, and cold. So galaxies will drift and nothing will be there which we can say can produce yet another celestial object. So yeah, this will lead to cold, dark, and empty universe. So these are the three predictions. Moving forward, limitation of the Big Bang model. So basically, our beloved Big Bang model does not explain a lot of things, such as why did Big Bang occurred at the first place, what triggered it, or what was before it. As in, we discussed about it that the time itself started after the Big Bang. So this reference of this age 13.8 is based on the reference that at Big Bang the time was at zero, which is kind of not possible because there must be something before it as well. At least I believe that. And also it does not explains the matter and dark and dark matter and dark energy properly, as in we can't see it, we just know it, something like that exists, which one thing which provides extra gravity and one thing which opposes gravity. We never saw any of them, dark matter of dark energy. We can just say it from its effect. And also matter antimatter asymmetry, it also remains a mystery. It was never solved before. Also, it does not explain why the laws of physics are the way they are. So there are a lot of unsolved questions in our way, and we hope that any one of you in near future will answer at least one of these questions. So these unsolved questions, like, can we have a unified theory combining quantum physics and gravity, known as the theory of everything? Or what happened during the Planck era? We don't have data for this Planck era, the initial time after the Big Bang. Why did matter survive, as in the matter antimatter mystery? Also, why is there something instead of nothing? There could just be like emptiness, but we know that universe is existing. Why it existed, it's still a mystery. Is our universe the only one, or are there multiverse also existing, or how can we scientifically prove that? And also, how will the universe end? It is still, those three are just prediction. God knows, maybe something different someday might happen and everything will end, or maybe everything will continue like this, who knows. So concluding the presentation here, there is a quote: every answer in science creates new question. The more we understand the universe, the more we realize how much remains unknown, and the greatest discoveries may still lie ahead. So thank you everyone for being a very patient audience, and your benign presence is being appreciated.